This session will focus on Hamiltonian graphs. Okay, so when it is possible to find a route along distinct edges of a graph that visits every vertex once and once only, then you have a simple circuit. Okay, so that is if it visits every vertex on the graph only. This problem is called a Hamiltonian circuit problem, and like Euler, it's also a problem of graph theory. So what is a Hamiltonian circuit? It's not enough to just visit every edge. You need to, like Euler, start and finish at the same edge. With Hamilton, you start at a particular vertex and you visit every other vertex on the graph once and return to the starting vertex. That is what constitutes a Hamiltonian circuit. So an efficient tour of the graph will be a route that started and ended at the same vertex, passed through all the vertices without reuse or repetition. If that's the case, you've just traced a Hamiltonian circuit. So we think of a circuit at starting, any circuit starts and ends at the same vertex. Okay, so knowing what a Hamiltonian circuit is, let's look at these two graphs. If we look at graph A and we say we started at vertex A, we then visited C, D, went to F, went to H, to I, to G, to D, to B, and back at A. So you can see that we do not use every edge in the graph. We just use every vertex. And the same with this one. We have A, C, D, B, I, G, F, E, H, and back to A. The only difference maybe here is this one has 1, 2, 3, 4, 5, 6, 7, 8, 9 edges that it uses to visit the vertices. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9 as well. So there's no difference there. But the difference could come in if we are working with a weighted graph, where there are distances or costs assigned to each of the edges. Okay, so Euler and Hamilton are similar in the fact that they forbid reuse. Euler works with edges, Hamilton works with circles. What we see now is the complete graph K42. It's a bipartite graph. Okay, so on the left hand side we have the first 4 vertices grouped together. On the right hand side we have the n vertices, or the 2 vertices grouped together. Now for generality's sake we named it M and N. So an example of one graph from a family of graphs that has no Hamiltonian circuit. The number of vertices M on the left is too many to just map once onto the 2 vertices on the right. So let's see. This was 4 and that was 2. We visit there once, go there, go here, go there, go back here, and there's no way without reuse to visit the last vertex. Well, let's see. If there was only 3 and there was only 2 on this side, we would start, visit that one, visit, visit, visit. Oops, then it does have a Hamiltonian circuit. So it seems for now we can do a conjecture that if the left hand side has one more vertex than the right hand side, then it could have a Hamiltonian circuit, the bipartite graphs. So if this was the graph K32, we could find a Hamiltonian circuit. Now the same here. We looked at the rectangular blocks, the grids that form networks in cities. And on this network, we have alternated the colors so that no adjacent vertex has the same color. So a graph that's used to model a portion of a city is what you're looking at. Since the graph reflects a block structure in the city, it is known as a grid graph. Okay, checking a network of traffic lights or fire hydrants can be what that graph is representing. Okay, so this graph, by the way, remember, has chromatic number 2. Okay, so let's see what else we can say about that graph. Note that in going in from one vertex to another vertex, you move from one color to the next. So whether you go that way, it's red, blue, red, red, blue, red, red, blue, red, the vertices alter in color. So since the colors alternate in a Hamiltonian circuit, very important, it follows that the number of vertices for each color would have to be the same if there is a Hamiltonian circuit in that graph. Well, if we pay attention here, there's 13 red and 12 blue. So there is absolutely no Hamiltonian circuit in that graph. And if this was a graph that inspected traffic lights, there is no most economic path that we can plot out. In other words, form a Hamiltonian circuit that would represent what's happening. Okay, so for a graph to have a Hamiltonian circuit, each vertex must be of degree 2, at least of degree 2 or more. Then there will be a Hamiltonian circuit. Now obviously the more edges a graph will have, the more likely it will be to form a Hamiltonian circuit. Let's look at an example. You are in Chicago for a holiday and you are planning to visit 3 other cities while in the USA. The matrix below provides you with the information about the distances between the cities you would like to visit. So you want to visit Chicago, Cleveland, Minneapolis, and St. Louis. Now just remember the previous matrix that we looked at here. This is an adjacency matrix again. The horizontal or the diagonal entries on this 4x4 matrix, it's a square matrix if we want to go there, is naught, because between Chicago and Chicago the distance is definitely naught, unless there's 2 Chicagos, but there isn't in the USA, there's only 1. So we use this information to draw the graph representing the distances and the routes. Now folks, I'm going to ask you to pause the video at this stage and to draw the graph that represents that information that you have on the screen. Quickly pause the video and then we'll come back to see if your intuition was correct. Okay, let's see what you did. That is what the graph looks like. It has to be a K4 graph. There's 4 cities to visit, and all the cities, for you to work out the most economic route, you'll have to have the K4 graph. So each city is adjacent to every other city on the graph. Okay, so we want to find the minimum cost tour that starts and ends in Chicago. Let's say you flew over to the US and you landed in Chicago, and that's where everything starts. Okay, so you want from Chicago to visit every other city once only. So another way of putting that question is to find the minimum cost Hamiltonian circuit. In other words, a Hamiltonian circuit with the lowest possible sum of weights to its edges. Okay, so let's see what the definition says, or the procedure. Sorry. For finding a minimum cost Hamiltonian circuit, how do we determine which Hamiltonian circuit is of minimum cost? There is a conceptually easy algorithm that we can apply, a step-by-step process for solving this problem. First of all, we generate all possible Hamiltonian tours that starts in Chicago. After that, we add up the distances of every tour we've generated. We choose the tours with a total distance as a minimum, and that is our result. So let's have a look. We generate all possible tours, we add the distances, and from there we choose a tour with a total distance being a minimum. Okay, steps 2 and 3 of this algorithm are really straightforward. It's just an addition and then to make a choice. Step 1 is generating all the possible tours that we can have for that matrix of distances. Now there's our graph that represents the matrix. What we will do is we will use the method of trees. Starting from Chicago, we can choose any of the 3 cities to visit after leaving Chicago. So an example would be, starting in Chicago, you can go to Minneapolis, you can go to St. Louis, or you can go to Cleveland. So let us now see how that works. Notice that because we can traverse a circular tour in either of two directions, though, the paths shown in the tree diagram are repeating themselves and do not correspond to different Hamiltonian circuits. Now we'll see what that means just now. Let's start our tree. Starting at Chicago, we go to Minneapolis, 425 miles, to St. Louis, 300 miles, or we could go to Cleveland, 349 miles. Now we are in Minneapolis. We've been in Chicago, so we either can choose St. Louis or Cleveland. We chose St. Louis, so if we were in St. Louis, we don't want to go back to Chicago. We can either visit Cleveland or Minneapolis, and we chose to visit Cleveland. When we were in Cleveland, then we chose to take our next tour to Minneapolis. It really doesn't matter in which order you do it, folks. At the end of the day, you're going to add up these and they will add up to the very same weight. So those distances are there. We do our third city, and the last city that we can visit if we were in Chicago, Minneapolis, and St. Louis is Cleveland. And for the other one, Chicago, St. Louis, Cleveland, the last city is Minneapolis. And for the third tour, the last city will be St. Louis. There's the weights or the distances, and then we return to Chicago where we started. Now that forms our touring circuit, or in the language of graph theory, that's our Hamiltonian circuit that we're going to follow. If we add all those weights, we see actually that the minimum tour, or the minimum distance tour, is the one that starts in Chicago, goes to Minneapolis, then to St. Louis, then to Cleveland, and returns to Chicago. Total miles 1,877. So among what appear to be 6 different paths in the tree diagram, let's just go back. You could have visited these in reverse. You could have gone Chicago, Cleveland, St. Louis, Minneapolis, Chicago. Or Chicago, Minneapolis, Cleveland, St. Louis, Chicago, and so forth. So you can work from the bottom of the tree back to the top, or from the top to the bottom. That gives you 6 different tours, of which the one tour doubles up. Each tour is the same as the next tour. So the 3 tours that you could have looked at then is those 3 that lie over there. They all start in Chicago and end in Chicago, and they are all Hamiltonian circuits. Okay, so note that generating the Hamiltonian circuit, we actually discard the distances at first. Okay, we create the Hamiltonian circuit, and then to find the optimal route, we then go and add the edges to decide which tour we are definitely going to take. Okay, so things to watch out for when you use trees. If we look at using trees, the order of the travel doesn't matter. If you start in Chicago, you can go to St. Louis or Cleveland or Minnesota, it doesn't matter. But the one with the minimum is the one on the left. Okay, so what is a complete graph? We move on. A complete graph, graph is called complete if there is exactly one edge between 2 pairs of vertices on the graph. Then we have a complete graph. So was this a complete graph? Definitely. Each vertex was joined to every other vertex, so it's a complete graph. Okay, so again, a graph is called complete if there's exactly one edge between each pair of vertices on the graph. So each vertex is then joined to every other vertex with an edge. Okay, so the graph alongside was a weighted complete graph. So it was a weighted complete graph with 4 vertices. Therefore, remember, we call it K4. Okay, so here, each vertex is connected to every other vertex with exactly one edge. There are 5 vertices, so this is the complete graph K5. If we call it K5, the implication is that you know it's a complete graph with 5 vertices. Okay, so the fundamental principle of counting is going to become important when we look at Hamiltonian circuits. How many Hamiltonian circuits are there in a complete graph that has n vertices? That is what we're asking ourselves. Well, let's have a look. The method of trees was a visual application of the fundamental principle of counting, a procedure for counting outcomes in a multi-stage process. Let's see how it works. We can count how many patterns occur in a situation by looking at the number of ways in which the component parts can occur. Okay, so in the previous one, remember, we had 4 cities. Okay, so from the 4 cities that we want to visit, we could create 3 tours. So what does the fundamental principle of counting say? It says in general that if there are A ways of choosing one thing and B ways of choosing a second after the first has been chosen, and so on, and Z ways of choosing the last item after the earlier choices were made, then the total number of choice patterns is the product A times B times C times D times E, up to multiplying with Z, if there was Z different ways. Now that makes sense if you know the alphabet. Okay, so we come back to our question. How many Hamiltonian circuits are there in a complete graph with n vertices? So in Kn, how many Hamiltonian circuits are there? Remember, the starting point is already fixed. So we remove the first vertex from the pot. How many vertices are left? N minus 1 vertices. So for n vertices can be arranged in n minus 1 factorial roots. From choosing the first vertex, there's n minus 1 factorial ways in visiting the other vertices. So pairs of roots correspond to the same Hamiltonian circuit because one root can be obtained from the other by traversing the cities in reverse. We saw that in our discussion about visiting the 4 cities. So n vertices can be arranged in a half times n minus 1 factorial Hamiltonian circuits because each of the vertices are connected to an edge. So you move along that edge then to visit the other vertices. So let's see the difference between those two. If we look at the first one, n vertices can be arranged in n minus 1 roots. It's not talking about circuits. Okay, n vertices can be arranged in a half times n minus 1 factorial Hamiltonian circuits. Big difference. The second definition talks about starting and ending at the same point. So analysis of the 6-city problem would require a generation of 6 minus 1 factorial divided by 2, which is then 5 factorial, which is 120 divided by 2, which is 60 tours. We can have 60 tours. But for 25 cities, now look at this. The 24 factorial divided by 2 is approximately, there's an A missing there, 3 times 10 to the power 23 tours. Now just to make sense of that, if these tours could be generated at a rate of 1,000,000 tours per second, folks, it would take 10 billion years to generate each tour for you. Okay, so just to put that in perspective, at the rate at which this can grow. So because it would take so long to solve large vacation planning problems, let's say you're going to Europe, you want to visit 12 cities. Can you imagine drawing a tree for that? Okay, it is sometimes referred to as a brute force method. That is trying all possibilities, the one we've just done. And we're trying to avoid the brute force possibilities. So, if we look at Hamiltonian circuits, folks, we are looking at something that's called the traveling salesman problem. Unlike the Chinese postman problem, we don't have to visit each edge, but we visit each vertex and we find the most economic way to get there. So it's a branch of mathematics concerned with getting governments and businesses to operate more efficiently. In short, we're going to call it TSP. So what is the traveling salesman problem? It involves finding the trip of minimum cost that a salesman can take to visit the cities in a sales territory once and once only, represented by a complete graph with weights on each of the edges, and starts and ends at the same city where the trip started. So helping the salesman is the nearest neighbor algorithm. Starting from a home city, we first visit the nearest city to the home city, and then we visit the nearest city to that city which has not yet been visited. We return to the start city where no other choice is available. So in the Hamiltonian language, where no other vertex is available, we return to the starting vertex. This approach is called the nearest neighbor algorithm. Okay, so now we have all that information. Let's continue and look at a Hamiltonian circuit that we can form of the 1, 2, 3, 4 cities. Apply the nearest neighbor algorithm, it says, by traveling starting from Chicago. Okay, so if we look at Chicago, the nearest neighbor will be St. Louis. Okay, so applying this algorithm to the traveling salesman problem in the figure quickly leads to the tour from Chicago to St. Louis. The nearest then is Cleveland, and then Minneapolis at the bottom, and then we return to Chicago. Okay, so that is a total of 2,040 miles that you've traveled, and we've seen that there's a possibility with less. Okay, so the nearest neighbor algorithm is something that we call in graph theory a greedy algorithm, because at each stage the best choice is made. So once you've left Chicago for St. Louis, you look at what's left and you make the best choice. It's a greedy choice. Okay, so based on the appropriate criterion here, if we were at St. Louis, for instance, we would go and visit Cleveland, because if we went to Minneapolis, it would have cost us, or it would have been, it would have been 562 miles, where Cleveland is 541. But then we only have one city left after Cleveland, which is Minneapolis, and then the return trip to Chicago. So there we go. For the greedy algorithm, we use 300. Then we're going to choose 349. Okay, then 425. But now the problem is that we have 3 vertices. We've already returned to Chicago that way. If we then choose to go to Cleveland, we have formed a circuit where Cleveland or Chicago or St. Louis has been visited twice. So we can't choose there. So the next one would be to choose the next side, which is 562. But once we're there, we have to return, remember, to Chicago. So going to Cleveland would mean that we visited Cleveland twice. So the nearest neighbor algorithm does not really help us to choose appropriate ways of completing the tour. So if we went from Chicago to St. Louis, from St. Louis to Minneapolis, from Minneapolis to Cleveland, and from Cleveland back to Chicago, it's 1,985 kilometers. Okay, so we've completed the circuit from Chicago. Now, in fact, if you look at that circuit, you could start at any one of the vertices. If you complete the circuit that way, you will travel 1,985, and we've seen one with less. Okay, so if we look at another journey from Chicago to Cleveland to St. Louis, then to Minneapolis, and then back to Chicago, we have the least journey, the journey that does not start with the shortest edge. Okay, that journey is the most economic journey, 1,877 miles. So yes, the nearest neighbor algorithm does get close to the optimal journey, but doesn't always guarantee you the optimum journey. So if we look at this graph, it's a connected graph, a complete graph, K5, okay? And if we start at vertex A and we apply the nearest neighbor algorithm, I'm going to ask you to pause the video at this point and apply the nearest neighbor algorithm that starts at vertex A. Once you've done that, unpause the video and see whether you completed the correct journey. Okay, let's see what you did. Starting from vertex A, we choose the nearest neighbor, and the nearest neighbor there seems to be D. Okay, so we will go from A to D. Now we are at D. D is 400 to E, 850 to B, and 8 to C. So we will then definitely choose DE because it's the shortest route. Okay, now we are at E. E, you can go to either A, B, or C. To A, it's 700. To C, it's 750. And to B, it's 650. Now, with the nearest neighbor algorithm, you definitely will go to B. Now, please notice, folks, we've got one vertex left, that we want to visit. And that is vertex C. Now, B is adjacent to all the other vertices that have already been visited. So our last choice will be to go to C. Now at this point here, we have a Hamiltonian path because we visited each vertex once only. We don't have a circuit. So from C, we have to return to the start vertex, which is AC, the journey, or CA, 950. Okay, so let's see the weight of that path. The Hamiltonian circuit is AD, DE, EB, BC, and CA, and its total weight is 3050. Okay, so if you've got that, give yourself a pat on the shoulder, but we're not finished. You're going to stop the video now, again, and you're going to try to start at vertex B and use the nearest neighbor algorithm to complete a Hamiltonian circuit. Okay, let's see if your choices were indeed correct. If we start at B, the shortest pathway from B is to C with 500. Now we are at C. C is adjacent to every other vertex in here. So the vertices that's left to visit is A, E, and D. D is 800, E is 750, and A is 950. So clearly we're going to choose CE. Now we are at E and we must make a choice to visit either A or D. If we visit A, it's 700. If we visit D, it's 400. So we choose D. Now we are at D. The only other vertex that we haven't visited yet before we return to the start vertex is A, so we don't have a choice, we have to visit A. Now from A, we've got to go back to B. And the Hamiltonian circuit is thus formed with, look at the weight is different, the weight is 2,800. Okay, it's a Hamiltonian circuit of weight 2,800. Let's try it one more time. You're going to start the journey at vertex D this time and use the nearest neighbor algorithm to plot out a Hamiltonian circuit. Pause the video now. Once you've finished, play it again, continue playing to see whether your choices were indeed correct. Okay, let's see what you did. If we start at vertex D, D is adjacent to all the other four. The shortest path, we've got a pathway to E that is 400, so we start there. Now we are at E. We can either go to A, B, or C. Going to A is 700, going to B is 650, and to C is 750, so clearly there is no choice. We're going to do 650. Once we are at B, we have a choice of A or C to visit. We only have two cities left. if this was a city problem to visit. The nearest one is C with 500, so we go to C. And the only way now is to go to A. That was the last vertex that was left. Now what we've just mapped out is a Hamiltonian path, visiting all the vertices. To make it a circuit, we need to return to D, which is 550 away, the starting vertex. So that Hamiltonian path is also 3050 in weight. Okay, so we see the most economic path to have taken was the pathway that weighed 2,800 in total, and that pathway started at the vertex B. Now I'm sure if you start with the other vertices, there's two more vertices that we haven't started with, you'll see some repeats happening there as well. Okay, so applying the nearest neighbor algorithm, starting at vertex A, we get the tour that is 2,800 in cost. Now we saw that there, starting at the vertex B. So if the vertex A, if we follow ADECBA, we get a tour that costs 2,000, that has a weight or cost of 2,800 miles. Okay, when we started at B, we had 3050. The tour was BCADEB, and we completed it by starting and returning to vertex B. Okay, so what is the sorted edges algorithm? How's this going to help us? And we can think about how it is different from the nearest neighbor algorithm. Let's see what the sorted edges say. The procedure says start by sorting in arranging order the edges of each, the weight of the edges of each graph in order, in increasing order. Okay. Then at each stage select an edge that has not been previously chosen of least cost. That, number one, there's two conditions, never requires that three used edges meet at a vertex, because a Hamiltonian circuit uses up exactly two edges at each vertex. So you don't want three edges going into a vertex. And number two, never closes up a circular tour that doesn't complete all the vertices. So in other words, you don't want to form a cycle. The algorithm that we're going to apply is called the sorted edges algorithm. Okay, so remember the conditions. Never requires you that three edges meet at a vertex, and then also don't form a circuit. Now if we look at our four cities tour here, choose an edge of least cost that has not yet been used. It does not require three edges meet at a vertex, and it never closes up a circuit tour. So that B actually, C is deficient, B should be at the last point. There's two conditions, that's what I'm trying to say. So if we sort our edges, 300, 349, 429, 541, 562 and 774. If we use them in that order, we use 300 first, so it's the side SC, then we use 349, which is Cleveland, Chicago. The next weight is Minnesota and Chicago. We have three edges meeting at that vertex, not allowed. Okay, so when the shortest edges are added in order of increasing distance, we have this coming to us, which does not, which is forbidden if we want to form a Hamiltonian circuit. If we then go for the next weight, so we skip 425, this one, and we choose the next one, which is 451, then we completed a cycle without having visited Minnesota. Okay, so that's also not allowed for the Hamiltonian circuit. So it looks like the sorted edges problem for a problem that is this small is really not helping us to find the most efficient tour. Let's see when the edges, yeah, we've said that. Okay, so if we now go back to this diagram that we have here, and we sort all the edges from the least weight to the most weight, and we start applying our sorted edges algorithm. Let's see if that gets us somewhere. The first one that we're going to choose is DE because it's 400. The next one is BC. Now notice there that BC and ED is not even close to each other, but that's how we select our edges with the sorted edges algorithm. The next one is 550, which is AD. The next one is 600, which is AB. So far, let me see. Yeah, we visited every vertex, so we've got a Hamiltonian path, but we want a circuit. Okay, so if we now go for the very next edge, it is EB. Now, folks, having put EB in, you can see at the vertex B, we have a valence of 3, or a degree of 3. There's 3 paths that are incident at B, not allowed for Hamiltonian, so we're not going to use that one. If we use the one after that, it is 700, which then forms the circuit AED, not allowed, so we're not going to use that side. So we go to the next side, and that is the side CE with a weight of 750. So those are the sides that form the Hamiltonian circuit using the sorted edges algorithm. The total weight corresponds to the minimum total weight that we got. So we were lucky in this case. It did indeed bring us to a Hamiltonian circuit of minimum weight. Okay, so although the edges selected by applying the sorted edges method are connected to each other at every stage, this does not always happen. For example, when we chose the first 2 edges, B and C, they weren't close to each other. They did not even touch. There were edges that could connect them, but they were not even close. The edges that we then selected was AD, AB, and EC, giving the circuit EDABCE, which is the same as the nearest neighbor circuit that started at vertex A. Okay, so these algorithms that we are applying are quick and dirty. We call them heuristic algorithms, methods for the TSP problems. Okay, they do not guarantee optimal solutions to the traveling salesman problem, but they do come close enough to an optimal solution. Okay, so folks, in our next video, we are going to focus on algorithms that help us find the minimum cost trees and locate minimum spanning trees. We're going to then discuss trees and minimum cost spanning trees that also work with vertices. Please remember to like the video and to subscribe to the channel below.